In this lesson, we are continuing our learning in the analysis of functions to now determine whether a function is increasing or decreasing or constant over an interval. And you see kind of the bullet points that I've given for you for what it means for a function to be increasing, what it means for a function to be decreasing, what it means for a function to be constant. And algebraically, if you're looking at that and it kind of doesn't make sense, then let me show it to you graphically. If it's increasing, then I'd be looking at a graph where if this is x1 and this is x2, obviously x1 is less than x2, but if it is an increasing function over this interval, then I'm going to have things going up between those two x values. Whereas if it is decreasing over that interval, again, obviously x1 is going to be less than x2, but what I'm interested in is the function values at x1 and x2. And if it's decreasing over that interval, then that's what the graph would look like. It would be decreasing at that interval. And if a function is constant, then it's staying the same. Okay, so from x1 to x2, my y value is staying constant. So that's what we're looking at in determining whether a function is increasing, decreasing, or constant. So here we're being asked to look at the graph to estimate whether a function is increasing or decreasing or constant, and to support our answer numerically. So looking at part 1a in this example, I would hope that you would estimate that my graph is decreasing from negative infinity to, it looks like about 2. But then it's increasing from 2 to positive infinity. And then I'm asked to support my conjecture. So what I want to look at is verify that from values going towards negative infinity up to 2, that I am in fact increasing in my function values. So approaching negative infinity, I might use x values of negative 10, and then getting closer to 2. So negative 10, 5, 0, and 2. And what we're doing now is plugging these values into our calculator to verify that my function values, or my y values, are increasing. And this is straight calculator stuff. So 2 times negative 10 to the second power minus 8 times 10 plus 5 is 125. Plugging in negative 5. I have 2 times negative 5 squared minus 8 times negative 5 plus 5 is 95. Plugging in 0, I have 5. Plugging in 2, I have 2 times 2 squared minus 8 times 2 plus 5, giving me negative 3. And what I've just supported algebraically is that this function appears to be decreasing from negative infinity to positive 2. now I want to verify or support that the function is increasing from positive 2 to positive infinity. So I already know that my 2 value of the function is negative 3. Going towards positive infinity, I might use 5, 10, and 20. So plugging in 5 for t, I have 2 times 5 squared minus 8 times 5 plus 5, that's 15. Plugging in 10, I have 2 times 10 squared minus 8 times 10 plus 5 is 125. And plugging in 20, I have 2 times 20 squared minus 8 times 20 plus 5, and that's 645. And the reason why that 10 gave me pause is because I had negative 10 having a function value of 125, and that seems a bit not quite right. So I'm going to double check that negative 10 value, because even teachers make mistakes. So 2 times negative 10 squared minus 8 times negative 10 plus 5, that's 285. So my apologies about that, but it doesn't change what I'm supporting. I'm supporting that it's decreasing. So looking at that negative 10 and the negative 5, doesn't seem quite right either. Let me type in that negative 5. Mrs. Clouse is having an off day. Happens to everyone. So 2 times 5 squared minus 8 times negative 5 plus 5. And, oh no, I just accidentally erased the 9 there. Okay, so that makes more sense. Okay, so even though I had a little hiccup there, I still supported what I saw visually, that my function values are decreasing from negative infinity to 2 and increasing from 2 to positive infinity. Looking at my next function, which happens to be a piecewise function, please notice that there's a typo on your paper. On the second part of the function, on your paper it says x is greater than or equal to 3.1. You'll see that on the screen I have corrected that. It's negative 3.1. Please make sure that you've corrected that on your note-taking guide as well. So I've estimated that it's increasing from negative infinity to negative 3.1. So some values I might use approaching negative infinity, maybe negative 15, negative 10, negative 5, negative 3.1. And then I find my function values. So when I plug in negative 15, first of all I have to realize what part of the function I'm plugging into. Because negative 15 is less than negative 3.1, I'm plugging it into the first piece of my piecewise function. So in my calculator I'm doing 3 times negative 15 plus 11 and getting negative 34. Plugging in negative 10 also into the first part of my piecewise function, I have 3 times negative 10 plus 11, giving me negative 19. Plugging in negative 5, I have 3 times negative 5 plus 11, and that's negative 4. And when I plug in negative 3.1, I have to plug it into the second piece of my piecewise function, because negative 3.1 is greater than or equal to negative 3.1, and I get positive 1.7. So what I have just supported in this first table is that from negative infinity to negative 3.1, my function values are increasing. And then I'm going to algebraically verify that from -1 to positive infinity, my function is staying constant. So I already know that my function value at -3.1 is 1.7. I might try 0, I might try 5, I might try 10. And then I realize I have nothing to actually plug into. The second piece of my piecewise function says that my function value is 1.7 whenever my x value is greater than or equal to -3.1. And all of these are. And so I've just supported my observation that the function is constant from -3.1 to positive infinity. Another thing that we're able to analyze in function graphs is whether a function has an extrema. And an extrema is just a maximum or a minimum point somewhere on my graph, and it can be relative, meaning it's the smallest value or it's the largest value within a certain range, or it can be absolute. It would be the largest or smallest value of the whole function. So one point that I want to emphasize is that when a function changes between increasing, decreasing, or constant, you see that we call that point the extrema. Okay, so in number 2, part A, I might estimate that I have an extrema at -1.5. When x equals -1.5, it would appear that I have a relative maximum at -0.5. It would appear that I have a relative minimum and at approximately 1, running out of space, at approximately x equals 1, it looks like I have an absolute maximum. So I've made my estimates, and I'm being asked to support that. So numbers that are close to -1.5 might be -2. Since I've got another relative extrema at -0.5, let me go ahead and plug in -1 as well as that -0.5. And I'm, once again, supporting this numerically by using my calculator and plugging these values in for x. Okay, so I have -16 plus 8 plus 12 minus 4. And that's 0. When I plug in -1.5, I have -5.0625 plus that -1.5, or that positive 1.5 cubed, and then plus (2.25 times 3) minus 3, and that's approximately 2.1. When I plug in -1, I've got -1 plus 1 plus 3 minus 2, which is 1. And so far, it would appear that I have supported that there is a relative maximum at negative 1.5, because when I went to the left of it, my y value was smaller. When I went to the right of it, my y value was smaller. That's what you're looking at. Continuing and plugging in this negative 0.5 in our calculator. Have negative 0.19. Going a little bit to the right of that negative 0.5, I have 0. And when I plug in 0, I'll just have 0. So once again, looking at this, compared to the negative 1 values and the 0 value, that is a relative minimum. That negative 0.19 is smaller than the two y values on either side of it. I have an absolute maximum at 1, so I'm going to check positive 0.5, positive 1, positive 1.5. So the verifying process of this is tedious, time-consuming, as you can see, but it is just basically using your calculator. So I'm taking this 0.5 and raising it to the 4th power, making it negative, minus the 0.5 to the 3rd power, plus 3 times 0.5 squared, plus 2 times 0.5. And I get 1.56 approximately. Plugging in 1, I have negative 1, minus 1, plus 3, plus 2, which is 3. Finally, when I plug in the 1.5, I have 1.5 to the 4th power, let's make it negative, minus 1.5 to the 3rd power, plus 3 times 1.5 squared, plus 2 times 1.5. And that gives me 1.31 approximately. And again, notice that that appears to support my estimate that this is an extrema. The function value at 1 is greater than the function value of either of the things that I found to the left or right of it. Part B of this problem, we're doing the same thing. We're being asked to look at the graph and estimate and classify any extrema. So going from left to right, looking at this graph, it appears that I have a relative maximum at negative 1, a relative minimum at 0, another relative maximum at maybe 0.75, and another relative minimum at maybe 1.75. and those are our estimates. And in order to support them, we plug some values in on both sides of these values, trying to make sure that things look like they're going to a maximum or they look like there's a minimum. So I might plug in -2 for x before I plug in for 0. Maybe a -0.5, because it looks like I've got a maximum at -1 and then a minimum at 0. So I'll plug in 0 as well. Maybe 0.5, 0.75, 1, 1.75, and maybe 2. So I've got all these values that I'm going to be plugging into the function. I start with -2. So -2 to the 5th power minus 2 times -2 to the 4th power minus 2 times -2 to the 3rd power. And if you're not using parentheses for this negative value that you're raising to a power, just be ready to have to do it again, because the calculator is going to interpret what you typed in. And it needs the parentheses to interpret that you're squaring a negative number instead of taking the negative of a square. Okay, so this is -54. Plugging in -1. -1 to the 5th power minus 2 times -1 to the 4th power minus 2 times -1 to the 3rd power plus 3 times -1 squared. And that's 2. Plugging in -0.5 next. We have -0.5 to the 5th power minus 2 times -0.5 to the 4th power minus 2 times -0.5 to the 3rd power plus 3 times -0.5 squared. And that gives me approximately 0.84. And again, keep in mind where our estimates were. I estimated that -1 is my first relative extrema, and it is a maximum. Notice that the value of 2 is larger than either of the values surrounding it. Continuing, when I plug in 0, I'll get 0. Plugging in 0.5, we have 0.5 to the 5th power minus 2 times 0.5 to the 4th power minus 2 times 0.5 to the 3rd power plus 3 times 0.5 squared. That gets me 0.41 approximately. And remember that we had estimated that 0 was a relative minimum, and it is in fact smaller than the two values to either side of it. So we're still looking good in supporting our estimates. Continuing with the 0.75. 0.75 squared. I'm sorry, not squared. To the 5th power. Minus 2 times 0.75 to the 4th power minus 2 times 0.75 to the 3rd power plus 3 times 0.75 squared is 0.45. Plugging in 1, I have 1 to the 5th power minus 2 times 1 to the 4th power minus 2 times 1 to the 3rd power plus 3 times 1 squared, which is 0. Again, this was an estimated relative maximum, and it is in fact bigger than the two values on either side of it. Plugging in 1.75 to the 5th power minus 2 times 1.75 to the 4th power, minus 2 times 1.75 to the 3rd power plus 3 times 1.75 squared is negative 3.88. And plugging in 2, which I hope will be the last value I need to plug in, I have 2 to the 5th power minus 2 times 2 to the 4th power minus 2 times 2 to the 3rd power plus 3 times 2 squared. And I get negative 4, which doesn't support my estimate of 1.75 being a relative minimum. So maybe I need to go somewhere between 1.75 and 2. Maybe I need to look at 1.9. So let's try 1.9 and see if we get something that confirms a minimum value somewhere in here. So I plug in 1.9 now to the 5th power, minus 2 times 1.9 to the 4th power, minus 2 times 1.9 to the 3rd power, plus 3 times 1.9 squared. And that's negative 4.19. So it looks like my relative minimum might be closer to 1.9 than it is to the 1.75 that I had estimated, because this value is smaller than this one, which is to the right of it, and this one, which is to the left of it. So my estimate was close, but I needed to kind of adjust it in order to actually support that there was a minimum there. And of course, there's a more precise way to do this. We can use our our graphing calculators in order to get a more precise relative or absolute extrema. So we're going to use the Desmos graphing calculator, since I know most of my students don't have a TI-84 Plus. So here we go. And the function is 7 minus 5x. Whoops. Minus 6x squared. And when I drag my graph so that I can actually see my extrema, I have a maximum at negative approximately 0.42. And I know that it's an absolute maximum because if you look at this function here, notice that it's a quadratic. And a quadratic will only have a maximum or a minimum. Remember from our previous lesson that if the coefficient of the x squared term is negative, we know that it'll be a maximum. And so our absolute maximum value is this y coordinate of 8.042. So let's come back to what the question was asking us. The question was asking us to approximate to the nearest hundredth the relative or absolute extrema of the function. Again, the absolute maximum is approximately 8.04. They also ask us to state the x value where it occurs, and the x coordinate was negative 0.42. And gosh, that's so much nicer than having to plug stuff into an equation. Just looking at the graph, I can identify where my extrema is. So remember, sometimes you'll have a scientific calculator, graphing calculator that you have access to, and sometimes you won't. So make sure that you're able to go to use whatever tools you have accessible. If you have a graphing calculator or you're able to use Desmos, make sure that you know how to use it. If you're unable to use a graphing calculator, then that's where this tedious process comes in. Pause your video for the Your Turn below. In this example, we're really kind of putting everything together and talking about when on earth will I ever use this? If I want to create the maximum value, what I'm trying to do is optimize something. And when I'm trying to optimize something, I'm trying to find an extreme value for it. And that's where these graphs come in. So in this problem, I don't even have an equation. I have to figure the whole thing out, remembering stuff from way back in geometry 2 years ago. So a couple of formulas about a cylinder, which was what this problem is talking about. It says that the total surface area of a cylinder is going to be 10 pi. So it does also say that it has a bottom but no top, and then it's giving us the surface area. So let's remember the standard surface area formula. So the surface area formula for a cylinder, and you see on the screen as well as in your notes that this example goes for a bit, so you might want to kind of follow along visually or write stuff down on a separate sheet of paper because it might take up more space than I've given you on your paper. I just didn't want to kill more trees than I had to. So the surface area formula for a cylinder says I've got 2 pi RH, and that's my lateral area, and 2 pi r squared, and that's my two bases. But in this particular problem, I only have one base. So I don't need the 2 pi r squared, I just need pi r squared. And I'm also told that the total surface area is 10 pi. And the problem is asking me to maximize the volume. Well, volume of a cylinder is pi r squared h. So I would hope that you'd realize I've got way too many variables going on here. So what we need to do is express one value in terms of another. All right, so what I'm going to do is get the h by itself in the surface area formula, and I'll get an expression for h. And then I'm going to use that expression for h in the volume formula, which will naturally become a quadratic, or some kind of polynomial actually. And then I'm going to graph that using my graphing calculator and find out my relative maximum that I'm interested in. All right, so looking at this equation, notice that I have a pi in each of my terms. So let's go ahead and divide the pi away. Goodbye, pi. And I said I wanted to get h by itself. So I'm going to subtract the r squared from both sides, and now I have 10 minus r squared equals 2rh. I don't have r by itself yet, so I'm h by itself yet, excuse me. So I divide both sides by 2r here, and I have that h can be expressed as 10 minus r squared over 2r. And now I'm going to take this value that I've just found for h, and I'm going to use it here in my volume formula. So my volume will equal pi times r squared times this 10 minus r squared over 2r. And I can think of this as being over 1, and that means that I can simplify this equation a little bit and reduce my r and r squared, so that now I have pi r times 10 minus r squared over 2. And so that's the polynomial that I'm going to type into Desmos and find a relative maximum for, so that I can find the dimensions of a candle holder that will maximize the volume. So you see here in Desmos that I've typed up the equation. I used x instead of r, and I have this graph. Now I can't see everything that's happening here, so I'm going to zoom out of it, and I'm going to zoom out some more. And here's my relative maximum. So at this point, let's make sure that you understand what this point represents. This point is telling me that when my r, my x value, is 1.83, I will achieve my maximum volume of 19.12 approximately. Okay, so my r is 1.83, so let's bring that back into our screen. 1.83. Is my radius, and I'm going to use that radius to figure out my height. Remember that we had this expression here giving us a value for the height if we know the radius. So we take that radius and we plug it in. And when I plug that into my calculator, I have 10 minus 1.83 squared. Calculator did not like that. Let me try that again. 10 minus 1.83 squared divided by 2 times 1.83. And that's approximately 1.82. And so I've found the dimensions of a candle holder that will have my total surface area that they gave me while maximizing its volume. Finally, the last topic that this lesson addresses is average rate of change. And I think you'll find that average rate of change is a welcome relief after looking at the last example. So you've seen the term rate of change before. Rate of change is a phrase that we used for slope in algebra a few years ago. When a function has a curve, however, we don't really talk about the slope of a curve, but we do talk about the average rate of change of a curve. So in this particular example, we're being asked to find the average rate of change of this function on this interval. So what you're basically doing is finding the slope of the line that's passing through this x. We got to figure out what the y coordinate is. And this x, we have to find out its y coordinate. Okay, so if it helps, think of it as a table. I've got 2 and 3 as my x values. I need to use my calculator in order to find my y values. 2 to the third minus 2 times 2 squared minus 3 times 2 plus 2 is negative 4. Plugging in 3, I have 3 to the third minus 2 times 3 squared minus 3 times 3 plus 2. And that's 2. So my 2 points that I'm finding the slope between are 2, negative 4 and 3, 2. You remember slope formula, I hope. M equals y2 minus y1 over x2 minus x1. So 2 minus negative 4 over 3 minus 2. My average rate of change, therefore, is 6. And that's it. Take a moment and work through the your turn below.